When you add a solute to a solvent, you make a solution. Salt would be the solute when we add it to water because it's the particles that are dissolving. If the solute and solvent are in the same phase, as in both liquids or both solids or both gases, then it's the one in lesser quantity. But when you have a solid and a liquid, the solid will be the solute, which means water is our solvent because it does the dissolving. And then the salt water is the solution. Remember when we talked about solubility rules, we said that you'll have this chart. All of the substances on the top are soluble, meaning they break apart or dissolve, unless they're with one of these exceptions. The ones on the bottom are insoluble or will stay together unless they're with one of these exceptions. So refresh your memory, remember that iron 3 nitrate. So we're looking for nitrate. Nitrate is here, and it says that nitrates are soluble and there's no exceptions. So that should be soluble. Ammonium phosphate, we can look at phosphate. Phosphate is here, and phosphate should be insoluble unless it's with ammonia or the alkali metals. Remember, the alkali metals are group 1A. So since it's with ammonium, it will be soluble. And the last one, mercury 1 chloride. Here's chlorides. And chloride should be soluble unless it's with silver, mercury, or lead. Well, it's with mercury, therefore it will be insoluble. Go ahead and pause the video and put X's in the ones that are soluble. If it's insoluble, you can leave it blank. Restart when you have those 10 done. So all of these should have been soluble except the first one, barium sulfate, because sulfates are soluble unless it has strontium, barium, mercury, or lead. And the last one, cadmium hydroxide, because cadmium hydroxide is a weak base. It's also listed here, hydroxides are insoluble unless it's with one of those, which it's not. So there's 3 types of solutions. We have saturated, unsaturated, and supersaturated. A saturated solution is when a substance has dissolved as much as it can of a solute at a given amount of water and a given temperature. So when you are adding sugar to your drink, when all the sugar is going to the bottom and no more is dissolving, no matter how much you stir, that's a saturated solution. So you can generally tell a solution is saturated because it will have solid at the bottom. An unsaturated solution is a solution in which the water or solvent has not dissolved as much solute as it could. So if I go to the restaurant and just add 2 granules of sugar to my tea, then that will dissolve and that will be unsaturated because more could dissolve. So if you add more and it dissolves, then that was an unsaturated solution. And finally, a supersaturated solution means that the water or solvent has more solute at a given temperature than it should. This is an unstable solution, which means you don't see supersaturated solutions very often. One example of a supersaturated solution is when you're making rock candy, you get a supersaturated solution of sugar, and then you have a seed crystal. That seed crystal will pull all the extra sugar out of solution, forming that rock candy. This is another example of a supersaturated solution. So in the flask, we have a supersaturated solution of sodium acetate. So in this solution, we have a supersaturated solution of the sodium acetate. All that extra sodium acetate is dissolved in the solution. So when that one extra seed crystal is added, it disturbs the equilibrium it was at, and all this extra sodium acetate is coming out of solution. This solution is not freezing, it's having all the solid come out of it. So now there's going to be very little liquid left and mostly solid. We will see that process in class. So think about the 3 ways that you can make something dissolve faster. So I'll give you a second to think. If you said if you heat it up, it should dissolve faster, you are correct. If you stir it or if you crush it up. So heating it, stirring it, and crushing it up, which increases the surface area, will make things dissolve faster. Instead of sugar cubes, we use granule sugar to make things dissolve faster. When you add sugar to tea, you don't just let it sit there, you usually stir it. You can change the solubility of a solid by changing the temperature. Solids become more soluble as you increase the temperature, while gases are going to become less soluble as you increase the temperature. If I want more of that sugar to dissolve in my tea, I need to heat that tea up. That's how you can make sweet tea, is if you have hot tea, you add sugar to it, and when it cools, then all that sugar will stay dissolved. Gases, you can think gases become less soluble as temperature increases because your soda, you want to keep that in the fridge. If you keep it in the hot sun, it's going to cause the container to explode because that gas is trying to escape the solution. So looking at all those lines, which of these is most likely to be a gas? Which one is becoming less soluble as we increase the temperature? If you said this bottom purple one, or cerium sulfate, you're correct. If one of these was a gas, then that would be the most likely candidate. Which of these has the largest increase in solubility with an increase in temperature? So we're looking for the one with the largest slope. So if you said calcium chloride, you are correct. Notice it has the largest slope in any given amount of time. On the first question, it says, how many grams of potassium chloride will it take to saturate 100 grams of water at 50 degrees Celsius? When solving these problems, the 100 grams of water is not going to make a difference as long as it's 100 grams. Because in the graphic, it's how much grams of solute for every 100 grams of water. They have to specify how much water because if you increase the water, more solute will dissolve. So since these are both 100 grams, I can ignore that, and I'm just looking for 50 degrees, how much potassium chloride will dissolve. So you follow it up until you reach potassium chloride. And so that would be around 44 grams. For the next question, it says if I have 100 grams of water, so again, don't care about that piece, saturate with 50 degrees, and it's cooled to 20 degrees, how much potassium chloride will precipitate out? So I'm starting at 50 and I'm going to 20. I'm still looking at potassium chloride. So at 50 degrees, it was around 44, and at 20 degrees, it's about 34. So 44 minus 34, 10 grams will precipitate out. So when you're asked how much will precipitate out, find how much will dissolve at the two temperatures and subtract them. If I was increasing the temperature from 20 to 50 and it said how much more would I need to add, I would need to add 10 more because that's the difference from 20 to 50. This next one has 300 grams of water. So we do need to pay attention to that because our graph is only for 100 grams of water. So we find potassium nitrate at 30 degrees. So 30 degrees and potassium nitrate. So that's about 30 grams. So 30 grams will dissolve in 100 grams of water. We want to know how much will dissolve in 300 grams of water. So you're setting up a proportion. You should show that work on your paper. Therefore, I should have 3 times as much be able to dissolve, or 90 grams. So on this next one, it says we heated that same solution to 70 degrees. At 70 degrees, we can get about 130 grams for every 100 grams of water. So in 300 grams of water, we have 390 grams. But it says, how much more would I need to add? Well, I was already at 90 grams, so 390 minus 90, I need to add 300 more grams of potassium nitrate to make it saturated again. All right, one more type of problem that you could see. It says if you have 80 grams of KNO3 dissolved in 100 grams of water, so I can ignore the 100 grams of water, at 50 degrees, what type of solution do you have? So 50 degrees and 80. So you're going to draw a point at those coordinates. And then you need to see which line are we talking about. We're talking KNO3. Well, KNO3 at 50 degrees should only have around 60 grams dissolved. But if I have 80 grams dissolved, that's more than it should have dissolved. So that is a supersaturated solution. So if the point is above the line you're talking about, it will be supersaturated. Had it been 60 grams, then it would have been saturated. And if it was 50 grams, then it would have been unsaturated, because you could have added more than 50 grams at 50 degrees Celsius. I'm going to pause the video and try this one on your own. Restart when you have your answer. So for this problem, we had 500 grams of water, and we were going from 80 degrees to 20 degrees, and we wanted to know how much would precipitate out. So you should have found the sodium chloride line, found 80 degrees, and saw that around 40 grams could dissolve. So 40 grams and 100 grams of water, but we have 500 grams of water. Therefore, 200 grams at 80 degrees will be dissolved. We need to do the same thing for our 20 degrees. So at 20 degrees, we can dissolve around 38 maybe. So 38 grams for every 100 grams of water. So 500. So 5 times 38 is 190 grams at 20 degrees Celsius. Your answers will be slightly different than mine if you'd said it was 39 degrees or 37 degrees. So as long as it's close to 190. And therefore, if I had decreased the temperature from 80 to 20, around 10 grams would precipitate out. Again, had you used different numbers, then your answer may not be exactly that same amount. Go ahead and pause the video and try this one on your own. Restart when you have your answer. So you should have found KNO3 and made your point at 60 grams and 50 degrees. That's on the line, therefore that's a saturated solution. Go ahead and pause the video and try these last two on your own. Restart when you have an answer. So you can dissolve 10 grams in 100 grams of water, but we have 300 grams of water, therefore 30 grams can dissolve. And for the bottom one, at 80 degrees and NH3, we have 10 grams can dissolve. Therefore, if we only have 50 grams of water, half of that will be able to dissolve, or 5 grams. Pressure has no effect on solids or liquids because their particles are already so close together. But when you increase the pressure of a gas, you increase the solubility. Again, think of soda. Soda is generally bottled under high pressure, and we keep it in the fridge. So gases dissolve the best under high pressure and low temperature. So you may want to make sure that you have this summary written down. So the only way to make more solid dissolve is if you increase the temperature. If you want to make more gas dissolve, you decrease the temperature and increase the pressure. So polar and ionic solids dissolve in polar solvents. So polar and ionic will dissolve in polar solvents, while nonpolar solutes dissolve in nonpolar solvents. The reason polar and ionic have a positive and negative side, which are able to attract, while nonpolar solvents don't. Miscible means that both the solid and solvent are liquid, and both liquids are soluble in each other. So they're going to mix. So miscible is mixable. That would be like ethylene glycol and water. They're all mixing together over here. Immiscible, not mixable. Two liquids that are not soluble in one another. So that would be like oil and water. Notice they're not mixing. They're forming two different layers. So miscible is mixable. Immiscible is not mixable. So on these types of problems, if you're trying to decide will the solute dissolve in which solvent, you've got to first say, are the solvents polar or nonpolar? Water, you should know, is polar. And CCl4 is symmetrically arranged with no lone pairs, so it's going to be nonpolar. Remember from the previous slide, we said that ionic and polar will dissolve in a polar solvent, so it better dissolve in water, while nonpolar solutes will dissolve in nonpolar CCl4. So NaCl starts with a metal, so that's ionic. Since it's ionic, it should dissolve in water. I2 shares its electrons equally. It's nonpolar, so it should dissolve better in a nonpolar solvent. Go ahead and pause the video and try these 6 on your own. Restart when you have finished those. Number 3 ends in hydroxide, but it's not a base. We don't have a metal in this. So it's only covalently bonded, and it's polar because of that OH at the end. So that would dissolve better in water. KNO3 is ionic, so it would dissolve in water. Calcium hydroxide, we have a metal in hydroxide, so that's ionic. Ionic will dissolve in water. Bromine is nonpolar, so it would dissolve better in CCl4. C6H6 only has carbon and hydrogen, therefore it's nonpolar. And FeCl3, we have a metal and nonmetal, so that's ionic, so it would dissolve in water better.